Hello everyone, thank you so much for coming. My name is Anh Pham. I'm very excited to talk today about examining the interaction between free living bacteria and iron in the global ocean. In general, I'm very interested in the interaction between microbes and nutrient cycling in the ocean. But today I'm just going to focus on the free living bacteria because bacteria can consume organic matters that produced by phytoplankton and zooplankton in the upper ocean, and they transform the organic matters into a more refractory form or remineralize the organic matters to release carbon dioxide and nutrients back to the water column. Also, bacteria can be eaten up by zooplankton, so bacteria can control the flow of carbon and nutrients in the marine ecosystem, and they constitute a link between ocean biogeochemistry and marine ecosystem dynamics. In the ocean, bacteria require nutrients like iron and dissolved organic carbon for their growth, and some studies have shown that bacteria can require much more iron than phytoplankton, and also in bacterial cell, the iron content can be much more than that of phytoplankton. So there is a potentially competition between bacteria and phytoplankton for iron. For that competition, bacteria can have an advantage because they do not require light for their growth, but they still depend on the dissolved organic carbon that produced by phytoplankton. So the question is iron a limiting factor for bacterial growth in the ocean? And what are the consequences of the competition between bacteria and phytoplankton for iron in the ocean? So to sum it up, today in this talk, I would like to address three scientific questions. How do free living bacteria modulate the ocean cycling of nutrients? I'm gonna focusing on iron. And second, how does the ocean iron cycle affect the growth of free living bacteria? Is iron can be a limiting factor for the growth of free living bacteria in the ocean? And finally, what are the consequences of the competition between free living bacteria and phytoplankton for iron? And to do that, I'm gonna use an ocean biogeochemistry model. I'm going to use the global model because I'm interested in global processes. I'm not going to go into details here, but basically the model represents all the cycling of all major nutrients like ammonium, nitrate, iron, and silicate. And the model also represents different types of phytoplankton, bacteria, and zooplankton. And using that model, I'm gonna first answer the question, how do free living bacteria modulate the ocean cycling of iron? I'm showing here results of the model. On the left-hand side is the bacterial iron uptake in the upper ocean from 0 to 100 meters. And on the right-hand side is the release of iron by bacterial mortality in the upper ocean. And we see that free living bacteria activities consume and release a significant amount of iron in the upper ocean, especially along the coastal regions in the high northern latitude, in the tropical ocean, and around the Antarctic circumpolar regions. But if we compare the release of iron by bacteria with the consumption of iron by bacteria, we see that bacteria consume more iron than they release in the upper ocean. So in the upper ocean, bacteria can act as a sink for iron. And second, how does the ocean iron cycle affect the growth of free living bacteria? I'm showing here on the left-hand side and on the right-hand side, the surface limitation status for bacteria in June, July, August, the growing season in the Northern Hemisphere. And one thing to note here is if we see a lower value for the surface limitation status, it means that this factor is going to be the limiting factor for the growth of free living bacteria. And we see that for DOC, the surface limitation status for bacteria is lower than that of iron almost everywhere in the ocean. So we can conclude that DOC, dissolved organic carbon, is the main limiting factor for the growth of free living bacteria in the ocean. But if we look at regions like the Northern Pacific, the tropical Pacific, and Northern Atlantic, we see that iron can emerge as a secondary factor limiting the growth of free living bacteria as well. And if we have a high iron requirement for bacteria, we're going to see the decrease of bacterial biomass in the tropical ocean, the North Pacific, and some areas in the Southern Ocean. So basically, the growth of free living bacteria is very sensitive to iron in low iron regions. And finally, what are the consequences of the competition between free living bacteria and phytoplankton for iron? I'm showing here on the left-hand side the contribution of bacteria to the total biological uptake of iron in the upper ocean, and we see that bacteria can contribute to around 0.3 to 0.6, 30 to 60% of the total biological uptake of iron in the upper ocean. When we have high iron storage for bacteria, we can decrease the magnitude of the seasonal cycle of chlorophyll in low iron regions like the Southern Ocean, tropical Pacific, Pacific and North Atlantic. So there is an active competition for iron between bacteria and phytoplankton in iron limiting regions. That's can that's gonna be modulating the phytoplankton blooms, and that's gonna have an important implication for the dissolved organic carbon production by phytoplankton. As we see here, when you have high iron storage for bacteria, we're gonna see the decrease of bacterial biomass in low iron regions. That is because when you have an active competition for iron between bacteria and phytoplankton in iron limiting regions, that's going to modulate the carbon production and phytoplankton blooms, and that's going to lead to a decrease in the available dissolved organic carbon for bacteria, and that leads to a decrease in the bacterial biomass. So we see an interesting interaction between microbial communities because of the competition for iron between bacteria and phytoplankton. So to conclude, I have three answers for the questions that I put out. First, free living bacteria consume a significant amount of iron in the surface ocean and compete with phytoplankton for this resource. Second, iron can emerge as a secondary factor limiting the growth of free living bacteria in low iron regions, with EOC is a main limiting resource. And finally, active competition for iron between microbes in iron limiting regions can modulate phytoplankton blooms and carbon production, and that's going to lead to an interesting interaction between the microbial communities. And with that, I would love to take any question, and thank you for your listening. I also would like to thank my collaborators, Olivia Mong, Alexander Traklibiri, Lavenia Ratnaraja, and all the people in Daniel Benkin's lab at UCLA. Thank you so much.